Okay, this is going to be the set of notes on entropy, which we just introduced here today. And you can see here that it has to do with the disorder of things in the universe. So the first question we ask is, like, what is entropy? It's another one of those nonsense science words that we're introducing this unit. And you can see here, it's a relative measure of the disorder within a system. And, thinking of it just as disorder probably isn't going all the way in terms of the scientific definition. So here I've given you like more of a technical scientific definition. It says if a system can exist in a large number of states, it has high entropy. And so I'm going to go through an example of something and explain what I mean by a large number of states. And then the last thing here to get put into your memory to memorize is that S is the symbol for entropy. So it's another one of those letters that doesn't really match the name, but you're going to have all of these memorized for the test here this week. So yeah, S is entropy, H is enthalpy, Q is heat. So this is that example I told you about where I'm going to try and explain about what I mean by different states. So we have a situation here where we've got $1, and I'm saying that you can't split it up in any way. So it has to remain $1, and only one person can have it. And I'm asking how many different states are there for where this dollar can be, basically. And if you think about it, you'll see like there are only 3 possible states. Person A can have the dollar, person B can have the dollar, or person C can have the dollar. Someone in one of my classes today mentioned that there could be another state wherein nobody had the dollar, where the dollar was just discarded, and I thought that was actually a pretty savvy thing to say. And assuming a universe where that was possible, then that would be another 4th state. But in this case, we're saying, like, we're assuming a universe wherein somebody has to have the dollar, and it can't be split between any of them. So there's only 3 possible states. Okay, so now we're going to do another thought experiment. This time there's a 4th person. You should be able to pretty easily extend that logic to see here that there would be 4 possible states. And so if we add another person, basically we're adding another place for that dollar to go. And so you get more entropy here because there's an additional possible state, an additional possible location for that dollar. Continuing on with the thought experiment, I'll say, like, what if we had $2 then, and we were thinking about how we could distribute this between these 4 people? Well, there are now 16 possible states. And in order to do this, you have to think about the fact that the dollar bills would actually be unique and identifiable. So each dollar bill has something like a serial number on it, or it might be crumpled or stained. You can tell one dollar bill from another dollar bill. They're not exactly the same. So it makes a difference which person has which dollar bill. And so you can see 16 possible states for this one. So by adding the additional dollar, we're getting more entropy as well. And so again, it's directly related to the number of possible states. That's the definition of entropy. Okay, so another way of thinking of it when we're talking about chemistry is dispersal of matter energy, and the larger area it's dispersed into, the more entropy there is, because this is like when we had that 4th person and we had more space for the dollar to move into, and so the more dispersed things are, the higher the entropy, the more possible states there are for them. And so here I've got a little graph that shows how things can be dispersed. State of matter, the way that's dispersed is solids are really, they're really fixed into place, so they vibrate a little bit in place, but they can't really move around very much. Liquids can kind of flow in and out of each other, so there's a lot more movement possible with liquids, so they have higher entropy. And then gases fill their container, and so those can expand to whatever volume the container is that they're in. So those move all over the place, and they have a tremendous amount of entropy compared to liquids. The next thing I say is number of pieces. So if you think about a situation where we have, say, a synthesis reaction where 2 molecules will come together to form 1 molecule, well, that decreases entropy if 2 things come together to form one thing. or if you have a decomposition reaction where one molecule will split into two separate molecules, that is an increase in entropy. So by splitting something, we're allowing it to be moved separately, like the different parts to be moved separately into different places, and so that increases the number of states, like having extra dollars. All right, volume. Basically, with volume, the larger size that you have, the more possible locations something can be in. So that the larger volume would increase entropy as well. In terms of dispersing energy, usually we're going to think about that in chemistry in terms of the temperature. And so if something's at high temperature, it has a lot of different electron states. So an electron can be excited to different energy levels, and the number of energy levels that are accessible to electrons goes up if it's at a higher temperature. And so it gains entropy at a higher temperature because the electrons have lots of different places that they can be. Also, having faster motion of particles means that there are more possibilities for where the particles can move, and that would increase entropy as well. So here's a little test to see if you understand the concepts. So we've got two different things here, an iron ingot at 60 degrees Celsius and an iron ingot at 30 degrees Celsius, and think about which one has more entropy. So on each of these, I'll give you like 2 or 3 seconds. Pause the video if you want to think about it for yourself, and then go on. So on this one, think about it for 2 or 3 seconds. Okay. Is the one at 60 degrees. The reason for this is because it has a higher temperature. So as I said, higher temperature means that there are more accessible electron states, and also the particles are moving faster, so there's more locations available to them. Okay, now think about H2O liquid versus H2O gas. In this case, it's the gas. And this is because gases are moving all around their containers, and so they have a lot more freedom of motion than liquids do, and so there are a lot more possible states that they might occupy. This next one, NaCl solid versus NaCl aqueous, you probably just saw that flash up there, so I'll just go ahead and reveal that one. This is aqueous. The reason for this is because aqueous means dissolved in water, and so if we have salt, and it's solid salt crystals versus salt that's dissolved in water, when you put it in the water, it's going to sort of spread out through the water, So again, thinking of it in terms of dispersal, the salt is going to be more dispersed if it's mixed in with water. The next one here, we've got a large container with 6 particles in it and a small container with 6 particles in it. So go ahead and think about that for a second. All right, and in this case, it's the large container. Again, just because there's more places that those particles can occupy, so there's more entropy in that situation. All right, now we're thinking about this reaction and asking what has more entropy, the products or the reactants. So look at it, think about it for a minute, maybe pause the video. All right, if you thought that the reactants had more entropy, you're correct. The reactants are gases, whereas the product there is a liquid, so that's one thing. And gases have more entropy than liquids. The other thing is, if you notice, there are a total of 3 molecules on the left-hand side. There's 2 hydrogen molecules and 1 oxygen molecule, versus on the right-hand side, we have 2 water molecules. So 3 molecules on the left, 2 molecules on the right. Having it split into more molecules means that there are more combinations and more distributions possible. So having more pieces or more molecules or moles would increase the entropy. So there are 2 reasons why the reactants have more than the products in this case. Okay, now I'm going to go on to talking about the second law of thermodynamics. This says the entropy of the universe is always increasing. This is perhaps one of the most fundamental laws of nature in terms of science. So any process, any action that you ever observe, the entropy of the universe increases as a result of that process. And that's kind of interesting, because there aren't a lot of things in science where you can be so sure about it 100% of the time, like law of conservation of energy and things like that, of course. But in this case, having something always be increasing all the time is kind of a unique situation with entropy. And so the side effect of this is that we mean the universe is going to be dispersing. And so as entropy is always increasing and increasing and increasing, the universe is going to be spreading out and breaking apart and things like that all the time. The other thing here is that we know that any spontaneous reaction has to have an increase in entropy of the universe. This is just a restatement of that second law of thermodynamics. And to understand that, you actually have to know what the word spontaneous means. So spontaneous means that something is going to occur without any external input of energy. And when I say external, I mean outside of the system. Okay, so looking at this process here, this is a reaction for the combustion of hydrogen gas, and I'll tell you that this is a spontaneous reaction. This does occur by itself, and the question is, how does this happen spontaneously? Because if you see on the left-hand side has more entropy. The reactants have more entropy than the products, and you might think, if the reactants have more entropy than the products, why do the products get formed at all? The key to that is looking over at the delta H. Delta H here is negative, which means that it's an exothermic reaction. Exothermic means that it's releasing heat to the environment. So exothermic reactions actually increase the entropy of the universe by releasing heat or dissipating heat outward to the environment. So in this case, this is a spontaneous process because along with the decrease in entropy we have from going from hydrogen and oxygen molecules into water molecules, we have an increase in entropy that is greater by releasing extra heat into the environment because it's an exothermic process. So you can read that explanation right there below. So one last thing that I have to say about this is you might wonder why the universe proceeds towards disorder or proceeds in the direction of more and more entropy. Well, there's not really a force that's pushing it that way. What it is more is just that, things spread out because as they move outward, and as more states become accessible to them, it's just way more probable that they're going to land in some random configuration than they're going to land in some sort of organized configuration. And so imagine that you have a deck of cards and you're just dropping them onto the ground. There might be a situation wherein you drop them and they land on the ground perfectly in a stack, going from ace of spades to two of spades to three of spades all the way through. And that would be a highly, highly ordered system. But that seems pretty darn unlikely. What's much more likely is that they're going to land on the floor in some sort of a random alignment, not even in a nice pile, but just like scattered over the floor, some of them facing up, some of them facing down. And because there are so many more random orders that you could have rather than having some sort of like specific organized pattern, the randomness just ends up winning out in the end. So that is why our universe ends up proceeding towards states of more entropy all the time.